Okay, hi everybody. Just wanted to do a quick video answer key for the organic problem set. So let's just look at it quickly. For problem number 1, you were asked to identify each of the following as an alkane, alkyne, or an aromatic hydrocarbon. I'll actually want you to do more than just those categories, but anyway, here we are. We can do the rest of them down here for this one. So we're looking for single bonds only, at least one double bond, at least one triple bond, and aromatic means you've got a ring that has alternating single and double bonds. It's actually more complicated than that, but that's the only definition that we have for this year. And then it says indicate for each whether it's saturated or unsaturated. Well, the only way you can be saturated is if you're an alkane. So everything else is going to be unsaturated from this list, because everything else will have some kind of double or triple bond or combination thereof and won't contain as many hydrogens as it possibly can. All right, so let's go through each one of these. The first one is A. You can see here in A that I've got a couple of ways that I'm representing it, right? I've got my single bonds and my double bonds represented here like we did when we were doing Lewis structures, but I've got some shortcuts here. I've got CH3s written here. You have to remember that carbon has the capacity to make 4 bonds, either 4 single bonds or 2 singles and a double, or a triple and a single, or 2 doubles, whatever. They have to add up to 4, okay? And when I just write CH3 like that connected to something else, that tells me that that carbon has only single bonds because it's bonding with 3 hydrogens. Hydrogen, of course, can only make 1 bond. So if I have CH3, that means there's a carbon. It has 3 single bonded hydrogens around it, and then whatever bond showing what it's connected to. Anyway, everything in this compound are single bonds except for that double bond right there. That tells me 2 things. It tells me it's an alkene because it has a double bond, and that also tells me that it's unsaturated because it does not have the maximum number of hydrogens that it could hold. It could, if I converted that double bond into a single bond, each one of these carbons would have the capacity to hold 1 more hydrogen each. So then it would be completely saturated, and then it would be an alkane. All right, but as it stands now, this has 1 double bond, therefore it's an alkene, and it's unsaturated. So let's look at the next one, C12H26. So C12H26, like, that looks like a lot, and you could say, oh my God, this is going to take me forever to write out, to figure out whether it's, all single bonds or if there's any double or triple bonds. But let me give you a hint, and you may not remember this because I think it was like one of the very first slides of this presentation, the presentation about chapter 25, but there's a formula that tells you whether you're dealing with an alkane or not. And you can see that formula if you look at this compound here. So it looks a little bit weird because it's actually E. This is the question for letter E. So let's look at this one. I think all of you could look at that and immediately say, wow, that's all single bonds. It's definitely an alkane. That's definitely saturated, all right? And that's true. So that's easy, but let's look at it. This has 1, 2, 3, 4 carbons. Each one of these carbons has 2 hydrogens, except for the carbons on the end. Both of them have an extra 3rd hydrogen. What that means is when you have an alkane, no matter how long or short the chain is, the number of hydrogens will be double the number of carbons, plus you'll have 2 additional hydrogens. So here I've got 4 carbons. That means I'm going to have double that number, 8 plus 2 bonus, that's 10. The formula for this would be C4H10. And the relationship between 4 and 10 is exactly what I just described. 10 is you take 4, multiply it by 2, and then you add 2. So if you look at this formula here, C12H26, now that you know this trick or remember this trick, you can quickly see, aha, if I double 12, that's 24, and then I add 2 to it, I'm going to get 26. So I don't have to draw out the whole thing. I just know from the ratio of carbons to hydrogens that this is made completely of single bonds. Therefore, it's an alkane. Therefore, it's saturated. All right. Now, For these two, you kind of do have to draw them out. I did not teach you the separate ratios for the other unsaturated alkyl compounds. So I actually, I'm not going to ask you to do anything like either one of these. But what you could do, actually, what you could do is you could look at them and you could say, oh, it's not this formula, therefore it must be unsaturated. You could definitely answer that question. But you might not be able to quickly, and this is meant to be done quickly, you might not be able to quickly tell me, does it have double bonds or does it have triple bonds, or is it aromatic? You would have to take some time and draw it out. So don't worry about those two. All right, E we've already done. F, this is super easy, propane. If you know your endings, ane means it's an alkane, done. I don't even have to draw it out. But you might want to practice drawing it out just because you should know that prop means it has 3 carbons. So that would be 3 carbons with 2 hydrogens on each and then 2 bonus hydrogens on the end. Basically just 1 carbon shorter than what we have here. That's butane. Okay, these two compounds are small enough to draw out. So you can really figure those out right away. Let me just get a different color here. So C2H2, right? That's all we have. So I've got 2 carbons and I've got 2 hydrogens. Now, the carbons, remember, are going to be making some combination of 4 bonds. Hydrogens can only make 1. So you could maybe propose that there's one hydrogen on each one of the carbons. Or you might also equally propose maybe one of these carbons has both the hydrogens on it. And then you would try to figure out, what's going on. You can probably quickly tell that this one won't work. This one won't work because this carbon already has 3 bonds. This carbon only has 1. And there's no way to have this carbon all by itself somehow creating 4 bonds. There's already 1 bond between it and the other carbon. You can't then draw 3 more for a total of 4 for 2 reasons. One, that doesn't happen. There's no quadruple bond. Second of all, then what would happen to this carbon? Then it would have 1, 2, 3, 4, 5, 6 bonds. That's also not going to happen. So you can kind of quickly figure out that, all right, that is not going to work. So we're going to go back to our original idea, which shows me, 1 hydrogen on each carbon. Now, I'm still not done because these carbons don't have enough bonds around them, but I have drawn all the atoms that exist. There's no more atoms than this. Also, the hydrogens are done. They can't bond anymore. So you've got to do something with these 2 carbons between each other that's going to make them feel like they each have 4 bonds. Right now, they each feel like they have 2, right? This carbon has 2, this carbon has 2. They both need 2 more bonds. Well, you probably see where this is going. I can just put a triple bond between these 2 carbons. Now, they both feel like they have 3, right? And then they each also have an additional bond out to the hydrogen. When you have a triple bond like this, that means you've got an alkyne, and for sure it's unsaturated. All right, you can do something similar with this one. You can draw it out and kind of play with it. This one would take a little bit longer. I probably wouldn't put something that long on the test. But similar to these other ones that I wouldn't put on, you could definitely say, okay, well, it doesn't have the right ratio of hydrogens to carbons, so I can tell you for sure that it's unsaturated. You could work out whether it's double or triple bond. But I won't ask you to draw out long formulas. The short one's fine. You can do that. You have time to do that. And this one is like a trick, right? I mean, it's a long formula, but if you know, that's the right ratio for an alkane, done. Okay, let's look at this last one. This last one, hopefully you remember this sort of notation, means that I have a ring and I have an alternating set of double and single bonds. And that's like a big red flag. You definitely know that you have an aromatic hydrocarbon. The fact that you have any double bonds in there at all means that it's unsaturated. So that's done. Now we've done that whole section up there. All right, let's do this next thing. Draw and name 3 isomers of C5H12. All right, what you're doing there is you're looking at your formula and I'm telling you that there are at least 3 different ways that these can be connected. Okay, so we're going to look at this formula and we're going to draw 3 different versions using exactly 5 carbons and exactly 12 hydrogens. By the way, you'll note that that is the ratio for alkanes because 5 times 2 is 10, you add 2 to it and you get 12. So I know that I'm going to use all single bonds. The very first thing you should always do is the easiest one of all. Just take all your carbons and put them in a straight row and then saturate them with hydrogens. Just put as many hydrogens as they will hold. So there you go. That's the easiest one right there. That is all my carbons straight in one row. They've got as many hydrogens as they will hold. Now, to get my isomers, really all I'm going to do is take one of these carbons and stick it on somewhere else on the chain so that my parent chain doesn't have 5 carbons anymore but has 4 carbons. And I'm just going to stick this group coming off of something else. And then I'm going to fill in the hydrogens as they should be. By the way, when you take this group and stick it onto another carbon, you're going to have to replace, it will have to take the place of one of these hydrogens, right? So you'll have to move that hydrogen back to where this carbon would be. So you're just switching places. So let's do that. Okay, so before I fill this in, I just want to show you what I did. I took my 5 carbon chain, I took off the last carbon, and I just stuck it on one of the middle carbons. Now I'm going to fill it in with all the hydrogen. Okay, my drawing isn't very pretty, but you get the picture, right? I've got 1, 2, 3, 4 carbons in my parent chain. I've got 1 carbon sticking off of it, and I've just made single bonds all around. So now I've got 3 hydrogens on my terminal carbons, that is the carbons on the end of the chain, just like I did before. But now I've got this side carbon that also has 3 hydrogens on it. And you might think, oh, isn't that going to change your ratio? No, it doesn't, because this carbon only has 1 hydrogen on it. It has 1 hydrogen here, but all of its other bonds are to carbons. So I still have the exact same formula, and I can check in case I'm not sure, but I should have C5H12. So I've got 1, 2, 3, 4, 5 Cs, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So I'm still doing what I'm supposed to do. These 2 molecules are isomers of each other. They have exactly the same formula. They have exactly the same mass. They're made of exactly the same number and type of atoms, but they have a different structure. That means they will have some different properties. So those are isomers. We've got one more to do. And to do this one, I have to break off another carbon and stick it somewhere. And then we're going to get into an issue, right? Because if I try to do the same thing, if I break off this carbon and stick it on to one of the other carbons, I've got to be careful which one I stick it to, right? So if I take this off, and it's already attached to this carbon. So if I take it off and attach it to that carbon, it'll be in the shape of an L, but it'll really still be this. It'll still be this compound in terms of I'll have a long 5 carbon chain again. So I can't just take it and stick it onto that. I can't take it and just stick it down here because that's exactly what I have right now. That won't be any different than what I have right now. I'll still have a 4 carbon chain with another group sticking off of it. So I can't do either one of those moves. If I take this and I stick it on the end of this one over here, then again, I'm just going to have my 5 carbon chain again. That's not going to be any different. And sometimes you can't tell that you're making something that's really just the same that you've already made until you sit down and try to name it. And that's why the naming is an important part of this exercise. So, I'm kind of running out of options because even if I take this end group here and I stick it on here, then I'm going to end up again with what I already have, because then I would have a 1, 2, 3, 4 carbon chain with something sticking off of the second carbon. So the only thing I can do that's different than what I've done so far is to pick one of my carbons and make sure that it has 2 carbons coming off of it. See, right now, all of my carbons are either surrounded by H's or this carbon has another carbon group coming off of it. What if I had another carbon group coming off of this one instead of that hydrogen? In other words, what if I took this and switched places, this CH3 group, and put it here, and took this H and put it there? Let's do that. So again, before I fill it in with all the H's, because it's going to get ugly really quickly, let me just show you what I did. We took this part of the compound, these 3 carbons here and the one in the middle having another carbon, and we took this one on the end and plunked that down so that we now have a central carbon that is surrounded by 4 carbons. I'm still using 5 carbons, and you'll see when I put all the H's around, well, you can probably already see each one of these carbons is going to have 3 hydrogens around it. Well, what's 3 times 4? That's 12. So I'm still going to have the same formula. Okay, so this one's kind of cool looking. It's got a nice symmetry to it. And this would be a fun one to build because all of these carbons are tetrahedral and they all have 4 single bonds around them. So this would be a cool looking object, despite my ugly drawing here. And it's still obeying the same formula. So what I have here are 3 different structures obeying the same formula. So they are isomers of each other. Okay, even though they seem like they would be identical, the fact that they have these different shapes means they're going to have different properties. And one of the things we find out is, you might remember this from the lecture, was that when you have these long compounds, if I had a beaker full of these molecules, they could stack on top of each other pretty easily and experience London dispersion forces, that Velcro force. And so it would be easier for a beaker full of these to freeze. And it would be harder for them to boil than it would for either of these. That's because these 2 molecules, especially this last one, have shapes that do not allow them to get close enough together to experience that Velcro force. And so what you get is the more branching you have off of a straight chain, and this is only branching, the harder it is to experience intermolecular forces, and therefore the easier it is to exist as a gas, and the harder it is to exist as a liquid or a solid. So those are some properties that we would see across those 3. Now, the next part is I've got to name all these. Well, naming these involves remembering what the base part of the name is, okay? And that means you've got to locate your longest carbon chain. Here it's super easy because it's just one long chain. That's 5 carbons. That means that's going to end in pent. We already know that these are all alkanes because of my ratio here, but now that I've drawn it out, I can really confirm these are all single bonds, so that's a pentane, okay? And that's really enough to identify this, although some people will call this N-pentane, like normal pentane, or some people will call it 1-pentane, just to emphasize the fact that there's nothing going on here, okay? It's enough for you to call it pentane this year, that's fine. Here I have my longest chain is a 4-carbon chain. Either I can see that one, that's the easiest one to see, but also this is a 4-carbon chain. It's just bent, but it's still a long continuous chain of 4 carbons. So it doesn't matter. I'm going to leave this one highlighted because it doesn't matter whether you count that or that as your 4-carbon chain. It's going to give you the same name because either way you have a 1-carbon group, which is called a methyl group, sticking off of your chain. The only decision you have to make is you got to tell me which carbon it's sticking off of. And you have 2 choices only. You can count 1, 2, 3, 4, starting from this end, or you can count 1, 2, 3, 4, starting from that end. And by now you probably know that our naming system favors the lowest possible numbers that you can do. So in this case, I've got, I would want to number it in such a way that this is carbon 2, because it can either be 1, 2, 3, 4, or 1, 2, 3, 4. So I'm going to name this carbon 2. That's going to be important for the name. And what's coming off of carbon 2 is this. This is a methyl group, okay? Meth is the prefix, is the root name for when there's only 1 carbon. Our chain, however, has 4 carbons in it, and the root name for that is bute. Again, this is butane because my longest chain is 4 and all the bonds are single. It's butane. But I need to tell you something about this butane because on carbon 2, it has a methyl group coming off of it. So I hope I've got enough room here. I would write 2-methyl butane. And you literally do write it all together like that, methyl butane, hopefully with better handwriting than I have. So what do we do over here? Over here, I'm going to look for my longest chain. And no matter which way you slice it, your longest chain is 3 carbons long. You cannot find a longer chain than that. It does not matter if you do those 3, or those 3, or those 3, or those 3, or these 3. It doesn't matter. The name is going to be the same. And again, it's an alkane, so I know that I'm dealing with propane. This is a type of propane. But I have to tell you what's going on with this propane. And it's pretty clear. There's no real mystery about numbering this 3 carbon chain. It's either 1, 2, 3 or 1, 2, 3. So either way, this is carbon number 2. What's different now is all the action is obviously on carbon number 2, but there's 2 things happening. I've got a methyl group up here, and then I have another methyl group over here. So in the name, I have to tell you to kind of look at carbon number 2 twice. And so one option, like if we were being robots and we were naming this, we might say this is 2-methyl propane. But that's dumb, right? Because you're saying the same thing twice, and there's surely got to be a better way to do that. Well, there is. There is a shorter way to do that. And what we do is we say, first of all, we say dimethyl propane to tell you that there's 2 of them. And again, it's all written smashed together like that. And what we say is look at carbon number 2 twice. Okay? 2, 2 dash dimethyl propane. And just a quick reminder, whenever you separate numbers from letters, you do it with a dash. Whenever you separate numbers from each other, you do it with a comma. And you don't separate letters from each other, you just smash them all together. So this is the point where you realize, okay, even though I've got the same formula, I've named these 3 things totally differently. That tells me that I definitely have 3 isomers because they're following the same rules in terms of what they're made of, but the way they're connected means I have to name them differently. And that's good because they do, after all, have different properties. Okay, that took a long time. While we're talking about naming, let's skip this for just a second. And let's go down here and look at this thing. Name the following alkane. Okay, so we know it's an alkane. So the first thing you've got to do is find the longest straight chain. Now this is going to be a little bit of a challenge because this thing is like folding and branching all over the place. So it might take you a while to find it. The longest straight chain means you put down your pen or your pencil and you don't lift it. Again, that's a chain. That's a continuous chain. Okay, so here's a 4 carbon continuous chain. That's obviously not my longest. Okay, here's another 4 carbon continuous chain. Not my longest because I can see that that's a long chain, right? That's 1, 2, 3, 4, 5, and that's not even the whole thing. There's some down here and there's some over here. So if you keep looking around and checking without lifting your pencil, you can see 1, 2, 3, 4, 5, 6, 7, 8. I actually can identify an 8 carbon chain. And you can quickly check if you want to, but you're not going to find anything longer than that. Let's see, 1, 2, 3, 4, 5. What if I go up here? 6, 7. Close, but not close enough. And I think you can see you're not going to find anything even that long. So the longest chain I have here is an 8 carbon chain. Okay, the next thing we need to deal with is numbering. So basically I've highlighted here my 8 carbon chain and I need to figure out, am I going to start numbering from this end or this end? Now, what decides the numbering system is which system is going to give you the lowest numbers overall, okay? You can check that quickly by seeing, okay, I'm just going to count along my chain and I'm going to, come on. I think it's frozen. Okay, I'm not sure what happened there, but you can see I've highlighted the chain and I'm going to count along the chain and I'm going to see, when's the first branching point at what carbon. And usually one end or the other will start at a lower number, and that's the number that you will use. In this case, though, we see that I can start over here and go 1, 2, 3. So I've got branching on carbon number 3 from this end, or I've got 1, 2, 3 branching on carbon number 3 in that end as well. So That doesn't help me decide which one is going to be the correct way. So I've got to look at all the other numbers and see what's going to give me, which numbering system is going to give me the lowest set of numbers. So again, here I'll have 1, 2, 3. I've got some branching here. Then on carbon 4, I have some branching. And then I have more branching on carbon 6. So if I number this way, I'm going to use the numbers 3, 4, and 6. Now let's count in the other direction. From this direction, I've got 1, 2, 3. So carbon 3 again. 4, 5, and 6. So here I've got 3, 5, 6. And in the other direction, I have 3, 4, 6. Very subtle difference, but we want the lowest set of numbers. So we're going to number from this end because that's going to give us 3, 4, and 6 in our name, and those are the lowest set of numbers. Okay, so you can see here that we've got an 8-carbon chain. That means the ending is going to be octane because it's an alkane and it's got 8 carbons. We figured out how we're going to number the carbons. And so now we've got to figure out like what's going on at each one of these. And it's pretty similar if you look at them. This carbon has a methyl group coming off of it. This carbon also has a methyl group coming off of it. And what do you know? This carbon has a methyl group coming off of it, but this carbon also has this group coming off of it. Now, this looks like part of the chain, but we've ruled that out. We know it's not part of this entire chain. So that means it's a group that's coming off. It's not a methyl group because methyls only have 1 carbon. This is a 2-carbon group, which means that's an ethyl group. So let's number the carbon chains and let's figure out how we're going to name this whole thing. Okay, so here I've highlighted and numbered the important parts of the chain. So we can see the numbering starting with carbon 1 here and going all the way around the chain to carbon 8 here. I've highlighted in green the 3 methyl groups, and I've highlighted in blue the ethyl group. Now, when we put the name together, we are bound by the rules of alphabetical order in terms of whether you put, ethyl or methyl first. Ethyl comes first because it starts with an E. Even though we don't see the ethyl group until carbon number 4, with everything else, so within an alphabetical group, you obey numerical order. So what that means is for my 3 methyl groups, I'm going to put them in numerical order. But for my ethyl group, that's going to come first, even though it's on carbon 4. So let's see what that would look like. So since we know ethyl substituent has to come first, and that's on carbon 4, the beginning of the name is going to be 4-ethyl. And then there's going to be some more numbers after that, so I can put a dash here. So we've got the beginning of the name, we've got the ending of the name. Everything else is about these methyls. Now remember when we were naming this one up here, and we could have said 2-methyl, 2-methylpropane, but that's too repetitive. And we shortened things by using commas on the numbers, and we used the prefix di to say that there were 2 methyls in the whole branching off of the main chain. Well, here I've got 3 methyls, so I'm going to use the abbreviation trimethyl to show that. But before I do that, I'm going to tell you which carbons these methyls are on, and they're on carbons 3, 4, and 6. And I'll write those numbers, and they will be separated by commas. And so there you have it. There's the whole name of this long chain of carbons. We have 4-ethyl, 3,4,6 trimethyl octane. And again, see how the end of the compound, all those names, all those prefixes and roots all just get smashed together in one big long word. Always I have a dash between any combination of numbers and letters, and I separate any numbers I have with commas. So 4-ethyl dash 3, 4, 6 dash trimethyl octane. All right, so the last problem on this particular page asks you to label at least 3 functional groups on the following molecule. This is similar to what I've told you is going to be on the test, but not identical. I'm not going to give you one big compound like this that has all these different groups and ask you to identify the groups. Instead, I'm going to give you a simple molecule with only one of these groups and ask you to identify the group. Because when it's a simple molecule and it only has one of those groups, then we can classify it as belonging to that group. And that's what I want you to do because that's the skill that's appropriate for this level. A complex molecule like this you don't need. However, just so you know, whenever an organic chemist encounters a large complex molecule like this, I can refer to different parts of the molecule as having these special functional groups. But for us, we'll have simple molecules that will have just one of these functional groups. Either way, you have to recognize them and name them now, so let's do that. So what do I even mean when I say a functional group? Well, it's something that's different than your regular old carbons and hydrogens. So for example, this whole group right here is quite interesting. That's not your regular carbons and hydrogens. Same thing with this group. Same thing with this whole group sticking out here. This group sticking up there. That little oxygen over by itself. And that oxygen out there. Now I'm actually not going to highlight that one. I'm going to take that one off because that wasn't on your list that you're responsible for. That's a ketone. We'll take that out. But all the other ones are on your list of groups of organic molecules that you're responsible for knowing. So let's go through each one of those. Hopefully you can recognize them. I'm going to point out the three that you should recognize from the lab, and that is carboxylic acid, the C double bond O, then OH, alcohol, which is just the O single bond H, and ester, which is the O single bond C, double bond O, single bond something else on the other side. So this is an ester, this is an alcohol, and this is a carboxylic acid. And you probably remember that from the lab that we did. You had to identify those three compounds. On this large complex molecule, what I say is the carboxylic acid group, the alcohol group, and the ester group. I can refer to different parts of this large complex molecule. In addition to that, I have this oxygen with two single bonds on ether side of it. That's an ether. And then anytime you see anytime you see nitrogen built into the structure of a compound, you know that that is an amine. Okay? And then the last one, you might have noticed these. I wouldn't have expected you to pick up on that necessarily, but here I have an alternating system of double and single bonds in a ring structure, and that is an aromatic system. So you can draw it out like this, or you can symbolize it by a circle inside a hexagon like that. That would be another functional group. You could have identified that, but I wouldn't have expected that. Again, this group over here, the ketone, is not on your list, so you don't need to know that one, but it nevertheless exists. All right, so now I've labeled them just so you can see them all together. Carboxylic acid up top, amine over here, ester on the bottom, alcohol over to the left-hand side, and then the ether over here in the corner. And then in the middle, there was no clean way to label that, but that would be the aromatic group. All right, so for this part, you're asked to explain what's wrong with each of the following names of alkanes. So you know right away that these are all wrong. The way to deal with this is, and by the way, there won't be a question like this on the test, but this is good practice for you. You look at these incorrect names, and then you write out what you think they would look like, and then check to see how you would name what they were trying to show you. So let's start with the first one, 3-methylbutane. The fact that it's butane means that I've got a 4-carbon chain, and I've written it here, 4-carbon chain. And it says on carbon 3, I've got a methyl group. So I just said, okay, what if this is 1, 2, 3, 4, and then I have a methyl group hanging off of that. Well, hopefully you can see, now that you've got it written out, you can see the problem. If you've got a 4-carbon chain and a methyl group hanging off one of the carbons, that would be carbon 2, not carbon 3, right? Because even though I've written it here from left to right, that's not how we would number it. We would number it so that it gets the lowest number. So that's the problem with that name. Then the next one, number B, letter B, it says 1, 3 dimethylpentane. So I write out a pentane, there's my pentane there. And this time, just for fun, I numbered it from the right-hand side, and then I put 2 methyl groups, one coming off of carbon 1 and one coming off of carbon 3. The problem with that is, if you have a methyl group hanging off of your carbon 1, you actually have a longer carbon chain than you thought. It means that you looked at an L-shaped chain and thought that only the straight part here, the long part, was the entire carbon chain. But remember, as long as you can trace it without picking up your pen or pencil, it means you've got a continuous carbon chain. So this is 1, 2, 3, 4, 5, 6. You've got a 6-carbon chain. And then you have to look at where this carbon is. Then you can number it from either that side or this side, and you can tell that you should number it from this side because that'll give me 1, 2, 3 methylhexane versus 1, 2, 3, 4 methylhexane. So by mistakenly thinking this is a branch, they mistakenly gave it the wrong base name as pentane, when actually this is a 6-carbon chain. It is a hexane. I'm going to skip over number C, or part C, for just a second and go to letter D, 2-ethylpropane. So when this person wrote this name, they obviously were referring to a 3-carbon chain, propane, and they're telling me that on 2, carbon number 2, there's an ethyl group coming off of it. Well, what that would mean is off of this carbon 2, you have another group of 2 carbons. And hopefully you can see right away that really means that this is not your longest carbon chain, this 3-carbon chain here, but rather a 4-carbon chain, either this one or this one. So this is actually a 4-carbon chain. This is a butane. And by the way, if you look, it's the same thing as letter A. It's the same compound there because we have 4 carbons in the chain, and on one of the carbons we have a methyl group coming off. And we know that from numbering that we have to number that as carbon number 2. So both letter D and letter A would actually be named 2-methylbutane. Both of these would. Okay, so let's look at this last one now. Letter C, 2-dimethylbutane. Okay, so it's a butane, so it's a 4-carbon chain, and we know that on carbon 2, there's something going on. This is a little bit more subtle, but what you need here is you need to have the number 2 written twice, because you're trying to tell me that there's 2 methyl groups on carbon number 2. And you can't look at carbon number 2 and say, okay, there's a methyl group and then there's another methyl group. So in order to avoid doing that, you tell me to look twice at carbon 2, and you tell me to say, okay, I would say 2, 2-dimethylbutane, and that tells me on carbon 2 I have 1 methyl group and then another methyl group, and now the name is correct. Okay, these last 2 are super easy. Remember, for problem number 6, I was only asking you to do A and B. Super duper easy now that we've been through the rest of this. Hexane, all that means is you've got 6 carbons and the appropriate number of hydrogens so that everything is single bonded because it's an alkane. And for the next one, methyl alcohol, that means you have an alcohol, so you're going to have an OH, and it's a methyl alcohol, meaning it only has 1 carbon. So you're just going to write 1 carbon, put an OH on that, and then fill in the rest of the carbon bonds with H's. Very, very simple. You're not required to do any of the rest of them because, well, although you could do letter D, now that I see it, 1-butene. That would be a 4-carbon chain with a triple bond coming between carbon 1 and carbon 2. I think you could do that.